Thank you, Mr. Demba.
Thank you.
Yes, Bart, I think we can proceed. Hello, Bart. Hello.
Yes, sorry.
Okay. I think we can proceed, Bart.
Yeah, very good. So yeah, that was the first part of the session that we had planned for the afternoon, was on bioenergy feedstocks. That's basically meaning all the materials, the organic material that can be used for the production of bioenergy. Get the thing back. We will be looking briefly at different types of feedstock, from lignocellulosic biomass to oil, sugar, starch containing resources, to livestock waste and other organic wastes, and finally some remarks on the logistics of making feedstocks available for energy production. I think we briefly managed to include this issue of the nature of bioenergy feedstock in one of the sessions yesterday. We're talking about biomass, bioenergy feedstock. We're talking about organic material, which was produced by growing plants, recently produced by growing plants, through the process of photosynthesis, meaning that sunlight is used for the production of organic material by plants, basically from carbon dioxide and water. And what plants do is they convert the carbon and hydrogen and oxygen to organic material, and those are the main chemical building blocks: carbon, hydrogen, oxygen, and in smaller quantities also other elements like nitrogen, sulfur, but also potassium, phosphorus, etc., which are needed for growth of plants. I think yesterday we already remarked that bioenergy as such is also a form of solar energy, but then let's say using organic material as an intermediate product. So we've shown this sheet. I think this is, as I indicated, one of the possible categorizations of bioenergy feedstocks. This is by source, basically. Say forestry, agriculture, industry, and households. On the other hand, it is about the nature of the feedstock: lignocellulosic, oil, sugar, starch containing wastes from livestock and livestock processing, and other types of organic waste, including wastewater. I don't know if there were any questions yesterday that we may have missed about this. Maybe it's good that after this first part we will have another set of questions, short period where people can pose their questions. All right, so starting with lignocellulosic biomass, which is probably the most important one. As we saw yesterday, a solid biomass like wood, but also like agricultural residues, and the largest part of stocks. On the one hand, because it is widely used for heat generation for biomass. But at the same time, increasing quantities are used for modern energy production, electricity and heat. So on the one hand, we see different like from energy plantations, whether that is wood or say sugar containing, starch containing, oil containing. And if we look at lignocellulosic biomass, then it's mainly used for so-called thermochemical conversion, thermochemical bioenergy production. And that is that includes combustion, gasification, and pyrolysis. Some common examples of lignocellulosic biomass are wood, woody biomass, fuel wood, treetops from forestry operations, slabs from sawmills. We have, on the other hand, we have agricultural byproducts, stalks, rice straw, material that's left on the land after harvesting. And we have different types of agro-processing wastes, including bagasse from the sugar industry, coconut shell, cashew shell, rice husk, cassava fiber, and press cake. Just a moment. There's some noise from one of the participants. Try to mute. Okay, thank you. So what are important properties of lignocellulosic biomass? We're looking at for example, wood, fuel wood. Well, we saw yesterday in one of the presentations that moisture content is a very important aspect, because it determines for a very large extent the heating value, the lower heating value, or the net calorific value of the biomass. We've seen that wet wood can contain more than 40% of water, has a really substantially lower heating value compared to dry wood or drier wood. Let's say 10-15% would be considered quite dry for wood. So that's very important to know, because if you're talking about a feedstock supply, then of course you need to know what it is that you're dealing with. How much energy do you need for the power plant? And if you know that, then you need to know the heating value of the biomass in order to know how much biomass you will need to collect or produce. So following from the moisture content, but also to some extent, let's say the properties of the biomass itself follows the net calorific value. So that's basically the amount of chemical energy per kilogram in the biomass. A third point is very important is the ash content, on the one hand, because it also relates to the heating value. If you have types of biomass with a lot of ash, and that means that this ash is inert. It doesn't contribute to the energy in the biomass. So if you have biomass with 20-25% of ash, then the heating value will be lower than if you have, like, for example, clean wood, which can have less than 1% of ash. Ash melting behavior is quite important, especially for combustion systems. And temperatures in furnaces can get really very high, and sometimes some types of biomass ashes start to melt at a certain temperature, and that means that you get quite sticky compounds which can cause fouling of boiler parts. Fourth point is morphology. By that we mean, let's say, the overall size and shape and bulk density of biomass. So whether we're talking about trunks of trees, branches, are we talking about wood chips? Are we talking about very fine biomass like the rice husk or chopped stalks? That's something that you need to know. To a large extent, this can be changed, for example, by chipping, milling, or briquetting. But these are additional steps in the conversion process that need to be taken into consideration. And also, this is important, of course, for the logistical aspect, because it affects the bulk density, and well, that's important for transport movements and storage as such. I have some examples, indications of different types of lignocellulosic biomass. Wood chips, dry and fresh. If I say fresh, then it can be even wetter than this 40%. It can be more than 50% at the moment of harvesting of wood. But usually within a few weeks, it already dries down to 40%. And well, then further drying takes either a very long time or has to be done by forced drying with heat and drying installations. We see bagasse, which is the pressed out sugar cane that is produced in the sugar production. Cashew nut shell, I'm sure that you can all imagine how that looks like. It's the residue after the nut itself has been taken out. Coconut shell, you all know, and rice husk, which is basically the small fibrous part which covers the rice grain as it is growing. You see quite some variation in the heating value on the one hand, in the ash content, and especially also in the bulk density. Can be quite low for dry wood chips. Rice husk even lower, and can go to even 5 times as much for coconut shell, for example. I have a very interesting tip for anyone who ever wants to know anything about the properties of biomass. I would definitely visit the village database, which is an initiative from the Dutch Energy Research Center. There's very many types of biomass included in this database, and plenty of properties like typical heating values, typical moisture contents, ash contents, and many more aspects. So that's really one to remember. Looking at energy crops, then we're usually talking about fast-growing woody or herbaceous biomass. and I thought maybe it's easiest to just give some examples. That can be eucalyptus, which is widely used. It's basically wood. Um, well, what is important for energy crops is the yield. So the average amount of biomass that can be produced in a year per hectare. And see that for eucalyptus, there's quite a wide range due to different conditions, soil conditions, climatic conditions, forest management conditions. Another type is what we call Lucina, which is also a woody type of biomass, which is harvested annually. So basically, once the branches are cut off, then they grow back up and they can be harvested again. And we have some types of herbaceous biomass, for example, miscanthus, which grows in the more temperate climates, and king grass, which grows in the more tropical and subtropical areas. It's very important to know that the costs of energy crops for biomass are usually substantially higher than when looking at byproducts or waste, because it takes quite an effort to produce this biomass. First of all, to make sure that you have the available land, prepare the land, then grow the biomass. Especially looking at eucalyptus, for example, where it takes quite a long time before the wood is actually mature and ready for harvesting. So let's say all of this, including the harvesting itself and the transportation, it really adds to the cost. So it's always advisable first to consider the availability of byproducts and waste. There are some very useful tips for conversion. One of them, I think, was also mentioned yesterday, is to calculate the lower heating value of woody biomass. What is seen is that there's not so much variation in the heating value of different wood species. On the one hand, because the composition in the elements carbon, hydrogen, and oxygen are quite similar for different types of wood. On the other hand, there is in most types of wood the ash content is quite low and quite constant. And that more or less leaves the moisture content as a determining variable. And that's why if you know the moisture content of wood, then it's quite easy to calculate within a certain margin of error, of course, the heating value, and possibly also the sheet that was shown during the technical concepts session yesterday shed some light on that as well. So basically, using this formula, you can see that wood with 40% moisture content would have a lower heating value of roughly 10 megajoules per kilogram, and if you have drier wood, roughly 15%, you'll be looking at roughly 15.4 megajoules per kilogram. And as I said, it doesn't matter that much what type of wood this would be. What is interesting to consider is what happens if biomass is being dried. Some types of bioenergy conversion do require biomass to be at a certain maximum moisture content. For example, some types of gasifiers or even furnaces, biomass furnaces, need to have biomass with at most 20 or 25% of moisture. Secondly, it's important for logistics, because every ton of water that is included in your biomass is a ton of water that you need to transport over a certain distance, and that if you can reduce that, then you lower your transport requirements. But what is at the same time important to realize is that overall there's not much of a change in the total energy. So basically, if you dry down 1 ton of wet wood down to, let's say, from 40% to 50% moisture, then on the one hand the heating value increases. Let's say the amount of megajoules per ton increases. But of course, if you lose tonnage because you lose a lot of water, that means that the overall mass reduces. So it more or less evens out. You get some small advantages, but this is relatively modest. So it's not like a silver bullet where you can say, well, if you dry your biomass, all of a sudden you get more energy out of it. That doesn't work like that. Well, there's some interesting formula here where you can calculate what your mass changes when you dry wood in combination with the formula here. You can see how the combination of lower heating value and changed biomass tonnage, how they relate together. Third one, the conversion of biomass to energy. Of course, that depends on how much biomass you have, so the tonnage. Secondly, the heating value of the biomass that you have, and thirdly, the conversion efficiency. And that conversion efficiency very much depends on the, let's say, the technology that you use for conversion, whether that is let's say combustion, gasification, pyrolysis, etc. And for a large extent also depending on scale, especially in the smaller scale of technology applications, you get quite some scale advantages in the increase of your installations. At some point, if you reach a certain capacity, then scale advantage for efficiency doesn't really apply anymore. For example, it doesn't really matter whether you have let's say a 500 kilowatt or a 5 megawatt engine for your biogas. The efficiency won't really be very different. The same with a turbine system of 10 megawatts or 50 megawatts. There's not that much of an efficiency increase. So basically, these formulas you can use for calculating the amount of energy that you can produce with a certain amount of biomass, or the amount of biomass that you need for producing a certain amount of energy. So it goes both ways. Just a small example. If you want to produce 2,000 megawatt hours in a year, so 2 million kilowatt hours, and you want to do that in a wood gasifier of 500 kilowatts, and you could say at that scale technology, you could have an efficiency of 24%. And you're using coconut shell, which is quite dry and quite dense, which has a heating value of 17 megajoules per kilogram. Then you can calculate how much of that coconut shell you need in a year. See, it says tons here, it should be megawatt hours, 2000 megawatt hours times 3.6 gigajoules for the heating value, divided by the lower heating value and the efficiency, the conversion efficiency. And then you get the tonnage of your coconut shell as an outcome of the calculation. I wanted to present this question to you. I don't know if we have enough time to work on this. What do you think, Carlos? Can we take 5 minutes to look at this question, or?
Well, I'm not sure. They should respond if they can take 5 minutes.
Okay, shall we give it a shot? I think it's not that different from what we saw in the previous sheets.
Yeah.
Basically, everyone who cares to participate. The question is, how much electricity can we produce with 1 ton of wood? Let's make it relatively fresh wood with a heating value of 10 megajoules per kilogram. And we convert this ton of wood in a electricity power plant, steam turbine power plant of 2 megawatts with an conversion efficiency of 18%. So my question is, how much electricity can you produce from 1 ton of this wood? Is that either 50 kilowatt hours, 500 kilowatt hours, or 5,000 kilowatt hours? Maybe, I don't know if we should be showing this sheet or, for example, this sheet.
Não sei se acompanharam a pergunta. Todos acompanharam a pergunta? Estão já a resolver? Can you display the question again, Bob?
Yes.
Sim. Liga o micro, por favor. Liga. Sim.
Dizia, penso que só estamos a fazer o acompanhamento, né, daquilo que está no slide. Mas, porém, prevalece alguma dúvida, né, na tabela número 2, né, que fala de lignos.
Tem que falar para o micro, não sou lhe ouvir.
Prevalece alguma dúvida na tabela 2, né?
Tabela 2.
Sim, lignos, células, biomassa, né?
Okay, the gentleman has got a question on table number 2. Table 2. Qual é a pergunta?
Por exemplo, vem a faixa de biomassa, né? Relativamente à percentagem e low high herting, né? Então, a esta percentagem, a que se refere exatamente? Porque para chegarmos à fase dos cálculos, temos que entender estes 40%, a que refere?
Aquele ash content. A percentagem está falando do ash content? Porque ali... Ou a percentagem, qual delas é que está a se referir?
Esse fresh wood chips.
Chips?
Yeah, fresh wood chips.
Chips,
sim, vem 40%.
15% é isso? A tua pergunta é o que representa 15%?
Sim, sim.
Okay, his question is what is the meaning of 15% on the wood chips, on the dry wood chips?
Well, basically, it means that every kilogram of wood chip contains 15% of water. Oh. So for 1 kilogram of wood chip, you will find 150 grams of water. Maybe the term dry is not well chosen here. Maybe it should have said dried, because you know, if we would say dry, then maybe you could think that the moisture content is 0%. And that is, you know, it's possible to do that if you use a drying oven, for example. But even in wood industry, if wood is dried, then it's you know, typically dried down to around 10-12%, sometimes a bit lower. But it's, you know, it's never dried down to 0%. So maybe indeed dried wood chips would be the better word here. But let's say the moisture content that is displayed, it's always indicates how much water, what is the percentage of water in the total biomass.
Deu para acompanhar agora? Aquela coluna é a coluna de percentagem de umidade. MC significa moisture content. Moisture content significa conteúdo de umidade. Conteúdo da água em qualquer um daqueles combustíveis. Então, 15% significa que o combustível tem 15% de água. Portanto, é preciso, se quisermos secar, temos que tirar dos 15% de uma percentagem de água. É o que significa. Okay? Thank you, Bart. We can go back to the question.
Okay. By the way, just one thing to add here. It's important. Please? Yes?
Can you explain
us? You have to add something?
Yeah, but I believe that there was another question.
Yes. Can you explain us the content?
No. Nothing else.
Material. For example, bagasse has 5% higher than coconut shell. Can you explain, please?
Well, on the one hand, it has to do with the nature of the material itself. So what elements other than carbon, hydrogen, and oxygen are included in the material. I have to admit, I'm not sure why bagasse, if bagasse has specific components like that, or whether this ash is due to let's say sand, for example, sand or earth that is present, dust, anything inert that is actually, you know, part of the stalk, and that when you you know, take out the juice from the cane, so what is left out is actually, you know, the biomass plus what dirt or what sand might be sticking to it. This is, for example, quite common in the wood industry. You have the outsides of tree trunks, which are sawn off in sawing machines. They get these slabs and the bark from the trees, and that has relatively high ash content, and that is partly because of let's say higher mineral content of the biomass itself, but also because, you know, during harvesting, especially, you know, there's a lot of sand and dirt that clings to the outside of the trunks. So it means that that adds to the ash content. Does that answer your question? Hello? Hello, can you hear me?
Yes, good. That's fine. Thank you.
Okay, thank you. So I think you had some time to think about the question that I posed. Is there someone in the audience who'd like to give it a shot? Anyone who made some calculations and?
Yes, I've calculated and I found B.
B. Okay. Could you tell us how you arrived at answer B? Could you explain how you calculated, how you made your calculation? You can do it in Portuguese if you prefer.
Okay. According to the formula provided on slide number 11, I put mass. We have 1 ton, 1,000 kilogram.
Yeah.
LHV, we have 10. Efficiency of conversion, we have 0.18. So it gives the result I found.
Okay. Does everyone agree, or are there people that arrived at a different conclusion?
Todos concordam com a opção B, que o colega calculou e explicou como calculou? Sorry? Yeah, room 205, 2 more people say yes, they agree with B.
Well, that's good, because indeed that's the right answer. 500 kilowatt hours. I don't have anything to add to the explanation. It's spot on. So thank you. Any questions about this or anything else? Shall we continue?
Alguém tem alguma dúvida, algum comentário que queira fazer? A resposta já foi dada e é correta. Eu queria saber neste exemplo, este 2 megawatts de steam turbine, o que é? There is a question here about, it's about the figure 2 megawatts E. What does it mean?
Sorry, that's just a suffix indicating that it's electrical output. Especially in bioenergy, you can also look at thermal systems, for example, production of heat, or combinations of boilers and turbines. And then for a boiler, for example, you could say megawatts thermal. It would be MW with TH as a suffix, and this indicates that it's electrical power output.
Percebeu, colega, a explicação? Não. Se tivermos, por exemplo, a lidarmos com uma caldeira que queima combustível para produzir vapor, em vez de termos MWE, teríamos MWTH. O MWTH diz megawatts de energia térmica, thermal energy. No caso, ali, temos o megawatts por energia elétrica. E significa eletricidade. Se apanhar MWTH, significa, portanto, energia em megawatts por energia térmica. Estamos a falar de energia térmica. Okay, Bart?
Yep. All right, so that was our lignocellulosic biomass. To have a look at the oil, sugar, and starch containing feedstocks. First, looking at the oil feedstocks, most of it is purposely grown. So, you know, I think we gave the example of the jatropha, which was quite extensively grown in Mozambique at one point. But also other oil feedstocks like palm oil is used for energy here and there. Soybean oil used for biodiesel. You have rapeseed oil, which is produced more in Europe. So those are purposely grown, let's say, energy crops. But other resources for oils that could be from waste cooking oil, for example. It's quite common to collect that for the production of biodiesel, particularly. Oil feedstocks are mainly used as engine fuel, either in their straight version, pure plant oil (PPO), or converted to biodiesel. I think we mentioned that yesterday in one of the sessions, that biodiesel is a modification of the oil so that it can be used in conventional diesel engines without any modification. But it's you know, it requires a chemical conversion step. Some examples are oil crops. Let's say palm oil, coconuts, jatropha, soybean, cotton oil, and waste oil, like I said, used cooking oil, but also in some vegetable oil refineries, you may have some injected batches. Let's say, for example, oils that have gone rancid, which can still be modified to be used as a feedstock for biodiesel production. And what is important to know is that different types of oil crops have different yields per hectare, and particularly palm oil is by far the at this point the most yielding oil crop that there is. Well, there's some other references like rapeseed and soybean, and they're not getting close to what can be achieved with palm oil. Although this yield is quite typical for Asia, 4.5 tons per hectare per year. I believe that in many other regions it can be lower. I think I'll skip this one. This is more about how oils can be used in the end for production of plant oil or biodiesel. We have some handy formulas here as well for conversion. On the one hand, for converting certain energy demands into a certain demand for vegetable oil. It's basically it's quite similar to what we saw with the lignocellulosic biomass. It's a matter of combining the amount of electricity that you need with the heating value of the oil and the conversion efficiency. I'll also skip the example for now. Interested participants can look at the sheets to make the calculation themselves. Looking at starch and sugar feedstocks, they are mainly used for the production of ethanol. And ethanol can be used as a fuel blend for gasoline, where, let's say, biodiesel can be blended with diesel. Ethanol, if it's really high grade, it can be blended with gasoline. And second major application is the use as household fuel. I think that's particularly for Mozambique that is the case. There's, I believe, a supplier of bioethanol produced from cassava. It can be used in specific ethanol stoves that can be bought on the market. Important examples of starch and sugar feedstocks. For sugar, we're mainly looking at sugar cane, sugar beet, and sweet sorghum. For starch crops, looking at mainly cassava and maize, and corn. Although, of course, other starch containing crops are possible as well. Potato, sweet potato, well, you name it. And looking at byproducts, I think especially sugarcane molasses is an important one. Molasses is a byproduct from sugar production, and it's quite a good feedstock for ethanol production. I think in many countries you see ethanol production units being constructed next to sugar mills, where the byproduct molasses can be used for ethanol production, and then the byproducts from the ethanol production can be used for biogas production. So we'll come to that later. I have here some indications of what you can achieve with molasses and with cassava, certain quantities, to make some sort of comparison, to have an idea of the quantities that can be produced in principle from a sugar mill, a capacity of 60,000 tons per year, which is, I think, a bit average for Mozambique. And from cassava, if you would have 1,000 hectares growing cassava roots, what amounts of ethanol could be produced. Third type of feedstock, livestock waste. It's very important for biogas production, particularly on household scale. There's around the world there's millions of small households digesters producing usually between 1 and 2 cubic meters of biogas per day, which can be used for cooking the meals for a household. And most of those are fed with manure, say livestock manure, cow dung, basically, to some extent also pig dung. Livestock waste also include slaughterhouse waste, specifically the wet waste, like the content of the stomachs of the animals that are slaughtered, to also the blood of the animals that is produced during slaughtering. Particularly dung is very widely used as a fertilizer, of course. It's used by families on small plots of lands, but it's also to some extent traded by larger farmers, and it's as such not really a waste. It's more like a byproduct. if you would be considering to produce biogas with it, then you have to put a value on the manure usually. It is important to notice that during the conversion process, the fertilizer value of the feedstock more or less remains the same. So, particularly the NPK in the manure or in the waste are not affected by the conversion to biogas. So using the residues of the biogas production, you can also use for fertilizing croplands. Important parameters of livestock waste are the amount of solid, where with dry biomass we look at the moisture content usually. With say wet materials like manure, we look at the solids content, because it's more or less the other way around. Let's say typical cattle manure, for example, would have roughly 85% of water and 15% of dry matter, dry solids. So it's usually expressed in terms of solid content. And then specifically looking at the organic solids content. So the solids will contain some portion of inert material, like sand, for example, which in solid biomass we would call ash. Here we would call it inorganics, or well, we could call it ash as well. And what is mainly important is the organic contents of the feedstock. For biogas, specifically, what is important is the amount of nitrogen in it. That has to do with the conversion process. If there's too much nitrogen in a feedstock, then you can get formation of ammonia, which is let's say at a certain concentration, it becomes an inhibitor, so a barrier for the bacteria that produce the biogas. If you have too little nitrogen, then the bacteria cannot reproduce. So that's that reduces the biogas potential, the amount of biogas that can be produced from that feedstock. The composition, whether it's actually convertible to energy. You do have organic material that converts very quickly and very easily to biogas. You also have types of material that convert very, very slowly, and particularly the lignocellulosic biomasses are less suitable for biogas. Although some herbaceous types of biomass, some grasses, some stalks, for example, straws, can be used for biogas production. But let's say it's not generally the first material that you would consider, and that leads to a certain, let's say, methane production potential. So let's say if you have a kilogram of material, then one of the attributes is, let's say, how much methane you can produce from that material. That's an important parameter, or important property. And this graph shows for a range of different types of feedstock how much methane can be produced. Some interesting ones that can be shown are flotation sludge and used cooking oil. Those are, let's say, high fat organic containing organics. Glycerin and seed cake also have let's say a very high grease content. Well, glycerin is of course a material that is quite related to fats. These are typical organic materials you would find in kitchen waste, for example. Let's say raw vegetable type of waste, market waste. Summer contents found in slaughterhouses. Some different types of energy crops, grasses, corn types, corn stalk, leaf of certain crops. These are, let's say, the animal excrements or the animal dungs. I'll leave the examples for what they are for the moment, otherwise we will take too long. Last category is let's say other organic waste, and that is a bit of a container type, because it contains different types of waste from industries and households, like waste waters, but also the organic parts of solid waste, municipal solid waste. It can contain, let's say, food waste, for example, from food processing industries, but also from sisal, for example, which is produced in Tanzania and Kenya. Well, there's plenty of different types, and here also it's mainly used for biogas. And when it is landfilled, then gas can be extracted from the landfill, and then you would have landfill gas, which is basically a biogas as well. If we look at wastewater, then instead of focusing mainly on the dry matter for calculating biogas potential, we would rather look at the so-called chemical oxygen demand and the biological oxygen demand. We'll discuss that later when looking at anaerobic digestion. But that is an indicator for how much methane can be produced from a certain type of wastewater. And then other properties like the total solids and the suspended solids, which are more important for the design of the wastewater treatment system. The composition in terms of other elements other than the organic compounds, the acidity, the pH, alkalinity, all parameters indicating how what are the living conditions for anaerobic bacteria inside the material, whether the material may have to be diluted, for example, recycled in a way within the system to improve the conditions for the bacteria. Important always to bear in mind whether something is a waste or a resource. People really tend to think that if you have certain types of waste and you can use it for energy production, that is a way of valorizing this waste, making it a valuable resource. And in some cases this is the case. But quite often, waste is waste, and the simple fact that you can use it for energy production doesn't mean that it is, for example, economic per se to do so. It might actually result in quite high production costs if you have waste that, for example, needs to be sorted out, or waste before it can be used for energy production, or whether the emissions from a power plant using waste need to be thoroughly cleaned, because otherwise, you know, if you put all types of materials through the chimney, then you would be causing some great pollution to the air. And you know, especially in Europe, for example, you have in many places you have waste combustion systems that do produce electricity, but because of the high requirements of the flue gas treatment and the ash treatment, it's not as if the revenues from this electricity production are enough to cover the let's say the waste processing costs. There's still a price tag, and actually these plants they have a gate fee. So I mean, if any waste company wants to have their waste combusted there, they still have to pay for the service. So it's not like the plant buys this waste or gets it for free. No, they actually need gate fees in order to be financially sustainable. On the other hand, there's plenty of cases where what is considered a waste by one person or one company or institution is you know actually a resource of another. You know, especially if the logistics are not too complicated, and it's a clean type of waste that can be easily converted, then it can be very beneficial for a certain bioenergy production unit to start using this waste, whether it's biogas or combustion. There may be opportunities to use the waste for the byproducts created in certain industries, for example. Finally, logistics. I only have the one sheet here, which may be a bit meager if you consider the importance of this aspect, because especially if you need to transport biomass, or you need to store biomass for extended periods of time, then these are extremely important issues to consider. On the one hand, because you know many types of biomass may not be easily transported, and if they are transported and they are very wet, for example, then you know you'd be transporting quite large amounts of water rather than fuel. You know, the infrastructure for transport may be lacking or very poor. And there's always a cost involved with transportation. So I mean that's quite obvious. Same goes for storage. It also comes at a cost. Important to consider the amount of let's say the volume needed for storage. So let's say the bulk density and the number of months or days or hours that the biomass needs to be stored. And important to consider whether some types of biomass can actually be stored for longer periods, or whether it starts, you know, rotting or being converted to methane spontaneously. You can have molds. You can have all types of problems with non-perishable or with perishable types of organic materials. I think we're at the end of this part. It's probably a good time for a break.